Eight viewers.
What's like against your highest screen?
Huh?
What's like against your highest screen of viewers?
I don't know. I never paid attention to it. So I'm gonna get started in a minute or two, but I just wanted to kind of go over like what my plan is for this. So obviously, if you guys have any questions outstanding of what I plan on doing, you guys can ask them because this is for you. It's not for me. But my plan is to start with Unit 6 and 7, so like the hypothesis testing, all that craziness, because that seemed to be rough for a lot of people. And then I'm going to go over the Unit 3 stuff, so the regression and the correlation and slopes and all that craziness. Then I'm hoping to get to like the distribution, so binomial and normal, and setting up confidence intervals for all that. And then that might take up a lot of time, so I don't know if we'll get to the rest of this, but I was also going to cover ordinal, interval, and ratio, and histograms and box plots and how those work real quick. And then if there was time after that, I would take questions that people had. So, but again, feel free to interrupt me if I'm like blabbing and no one's saying anything. So for the people that I'm a TA for, I sent out a little hypothesis testing cheat sheet thing. So I'm going to just kind of brush over that a little bit and kind of hopefully clear up the differences between the different types of hypothesis testing. So, are there any questions right now for anything? Or do you want me to just start talking and see if that rings some bells? Okay. Also, we have an online crew watching us right now, so that's cool, technology. We got 15 viewers.
Yeah. Sean, I don't know if you're doing it already, but to see like some.
Yeah. Let me see if that makes it. Is that better? A little bit? Okay. All right. Yeah. So we got 15 people or so watching us right now from far away, which is kind of cool. So Unit 6 was all about, and Unit 7 was all about hypothesis testing. There's basically, how many? I think there's 6 different types of setups, which I will go over real quick. So we covered testing for probabilities or proportions. We covered 1 sample means. We covered 2 sample means, so like the difference in means. Then we talked about goodness of fit, which is 1 categorical variable. And then independence, which is 2 categorical variables. And then we talked about also for correlations and slopes. So that's like 2 quantitative variables. Not going to be so heavily focused on because it's kind of you need the software to kind of do it. But I'll show you the setup for that as well. So, so first we did proportions, right? And with every single hypothesis testing, we always have a null and an alternative, right? We know this. So our null is HO, and our alternative is HA. So when we do it for probabilities, we use the P for probability, right? And then in the parentheses, we put either correct or success. It depends on the context of what we're talking about. So the coin flip example was the amount correct she got. Success would be the number of mice that complete the maze, like you saw in the homework. So I'll just put success here for now. And then this one, you do the same thing as well. So far they're matching. They're the same thing. Now, for the next part, the null is always going to be an equal sign. And this is in every case that we do. The alternative depends on the context of your question. So for probabilities, we usually are concerned with greater than or less than. We're not really concerned about like not equal to or less than or equal to. So depending on the problem, it's going to be either greater than or less than. I'm going to just put greater than for now. And then the number that goes after it is the probability that we'd expect in the world, right? So for coin flips, we'd expect 50%. For the mice, we expected 20%. So this is whatever the value in question we're talking about. So I'll do 0.5. And this will be the same as well. So these two are exactly the same except for the equal or the greater than. Everything else is the same. Make sense? Cool? Okay. So our statistic for this, the thing we find to test whether it actually, we pick one of these, is the expected probability of our experiment happening. So in a perfect world, we expect 50-50, and then we do an experiment, right? And we figure out what the probability of that result is from the experiment. So in the coin flip example, she guessed 80 out of 100, and we found using the binomial distribution what her probability was. And so that observed probability is our p-value in this case. Make sense? Following? Cool. Nobody's saying anything, so I'm just going to assume yes. So then we learned that with this p-value, we can decide whether or not we pick one of these. And so what is the value we compare that to? 0.05, right? That's our magic number. Yep.
What's p-value again?
So the p-value is the probability of what we observed happening. So we compare this number, it's going to be really small, like 0.01 or 0.08 or something. We compare that to 0.05. If this number is bigger than 0.05, we fail to reject the null. In normal terms, we like this one, if it's greater than 0.05. If it's smaller than 0.05, we don't like the null, reject the null, and we pick this one. Make sense? Cool. So depending on your situation, like probabilities, means, categorical variables, whatever, that's going to determine your setup here and the statistic you get for your p-value. But for every single turn, like every single situation, we're always comparing to 0.05 and making our conclusion based off that. So we're doing the same thing every time, it's just different context. Cool? Okay, so that's probabilities or proportions. Then we talked about the mean of one sample. So a one sample mean. I'm just going to put a 1 there. So in this case, again, we have our null and our alternative, right? But since we're not talking about probabilities anymore, whatever comes next has to be different. So we're now talking about the mean of some sample. This is a mu. Sorry. All right, we all know that's a Greek letter mu by now, hopefully. So usually this would be like the mean of the depressed people, or the mean of the alcoholics, or some other example. So we have a population, and we pick a sample. So in the homework, we picked the depressed people, and we picked the alcoholics, and we want to test whether or not this sample of people is different from the population. So if we were doing the depressed people, again, the null would be equal, right? Null is always equal, pretty much. And our alternative in this case is not a greater than or less than, because we just want to know if it's different. So in this case, we're going to have a not equal to, because we don't care which way it's different, we just care that it is. And then the value in question is the population value, because we expect them to be similar to the population. So I think in the homework, the population was 16.4 or something. So if they're similar, they're going to equal the population. If they're different, they're going to not equal the population. Make sense? Cool. So now in this case, we would find our t statistic. Right, we did the t-test with the depressed, and then the mu, blah, 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 blah. Yep. That's just the name of the sample, the depressed, like the depressed sample, it's fine. So we would find our t-statistic, and this has a fancy formula, which is on your formula sheet. So it looks like this. I'm just going to put, yeah. So this is what is given on your formula sheet. So in any case, we're always comparing what we observe to what we expect, right? So in this case, we have our observed probability, and we compare it to what we expected. So this is our observed value. So this is the observed sample mean. So this would be the mean of the depressed people. This would be our expected mean, which would be 16.4. So be observed minus expected. You'll hear that a lot. And then this is the standard deviation of either the sample or the population. Usually it's this whatever is given to you. And then this is the sample size. Okay. And then this has, let me just see here. My bad, it is not T. I'm a bad TA. This should be a Z, I believe. Yeah. I think. Yeah. Okay. So yes, this is a Z. So this is the same as the Z score you learned back in whatever unit. So you find your Z value, right? And you're given a little chart in your formula sheet that tells you what your cutoff point is. So I don't know how many of you have the formula sheet printed out, but if you have like a laptop, you can pull it up off Moodle. So this would be some number, let's say it's 1.72. Let's just imagine that. And if we're comparing to alpha equals 0.05, we're going to find the value that lines up in the chart here. And so we wouldn't go off the one-tailed row, we'd go off the two-tailed row because this is a two-sided test, right? I know I'm blabbing a lot, I'm sorry. So this is a two-sided test, and what we would do is we would find out where 1.72 lies on this chart. Yep.
What makes it a two-sample test?
Because we are using a not equal to. So this is a two-sided test because we care about both sides. Like, it doesn't matter which way it's different. So it's two-sided, whereas this is one-sided because we only care about one direction.
Okay.
Yeah. Yep.
When we're doing problems with using that table, when do we use the one-sided? Like, don't we usually always use the two-sided?
Yeah. You probably won't ever use the one-sided for Z unless like a special case happens, but I don't think you'll have a one-sided situation for this. Yeah.
Is sigma divided by the square root of n, is that the sample standard deviation? Like, is that what that comes up equal, or is that something else?
So this is population standard deviation.
Right.
If we didn't know what the population standard deviation was, we would use T instead.
Okay.
Because we don't know enough about the population, so then we'd use this would be an S instead of a sigma. Okay, so let's say I got 1.72 from this thing. And so if I look at my chart, let me just draw it out a little bit. So I'm doing the two-tailed ones, so 0.2, 0.1, 0.05, blah, 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 blah. And then I have 1.282, 1.645, and 1.960, etc. So the way this works is you find where this value lies in these values here. So in this case, we'd be right here, right? That's where 1.72 would be. And this helps us find our p-value. So because this value is between 0.01 and 0.05, we're smaller than 0.01, 0.1, but we're bigger than 0.05. And that's what we care about, right? So because we're bigger than 0.05, what would we do?
Not reject the null.
Fail to reject, right? So if I was over here, we'd reject. But I'm over here. So we're going to fail to reject our null. Does that make sense? Yep.
I don't get it because like if the number's in the middle, how do you know which side to refer to in order to reject or not reject at all?
So if I add more here, I have 0.02, and then I have 2.327. So there's more numbers, and we're getting smaller and smaller and smaller and smaller. So we know that this side is the big side, and we know that this side is the small side. So if we're right here, we're bigger than this column, and we're smaller than this. So if we're larger than 0.05, then our p-value is larger than 0.05. So we fail to reject. Yep.
So if it's greater than 0.05 or less than 0.05, we just always fail to reject? Or is it just
If it's greater, we fail to reject. And if it's smaller, we reject. Yeah. Yep.
The 1.72 in this case, that's the z.
Yeah, that's this thing.
So like in a problem, would you like say this is like how would that be brought up in a problem? You just state like that's 1.72.
So it would probably be something like the population mean is blah blah blah. The sample mean is something with a standard deviation of this and a size of this. And you would calculate your z-value using those numbers.
Oh, and that's it. Okay.
And yeah.
Okay.
Yeah. Yep.
So is he gonna give us this chart, or should we bring the, like?
So he will give you the chart of numbers, like the table of numbers that you need to know. And he does that for both t and chi-square as well. So any statistic you have to find, he gives you one. Yep.
So I don't understand, is that not a z-score? Or?
They're the same,
Okay,
but in this context, it's a z-value.
okay,
It's just the same formula.
okay. So when you're looking at a z-score, you wouldn't use the.
Yeah, so the connection between that is that we're assuming that the population is normally distributed. And when we were using z-scores, we were finding out what the standard normal value was. So the z-scores are based off the normal distribution, where if I draw my normal, if I calculate the z-scores for every single person in my sample or population, we're going to have a mean of 0 and do you remember that, like 68, 95, 99.7? So this is going to be 1 and or -1 and 1, and then -2 and 2, blah blah blah. So when we calculate these z-scores, we're standardizing the distribution to be around 0 instead of around 16.4 or something like that. Does that make sense?
Yeah.
Okay. Yep.
So you would say like P is less than 0.01, but P is greater than 0.05, right?
Yeah. Yeah.
Okay. Yeah.
So what I would say is that based on my z-value, we know that the p-value is greater than 0.05. All right. So we can make our conclusion. Yep.
Since the tail, the p-values are always getting smaller as you go to the right, so whenever you have like your z-score or your p-value, is it always that it's smaller than the number on the left, but bigger than the number on the right?
Let me see. Yeah, that is usually the case. So I can explain that real quick. The reason that these get bigger as the p-value gets smaller is because the discrepancy between the sample and the population gets larger, which means the sample is much more different from the population. So that's why the numbers get bigger and the p-values get smaller. All right, good? Okay, so that is the one sample mean. So we did probabilities where we got our observed probability, and that was our p-value to compare to what we expect. And then here we compare our observed and expected to get a z-value, and then we just use the table to make our conclusion. Yep.
That stands for probability, not proportions.
They're one and the same.
Okay.
Yeah. Yeah. All right. So that was kind of like unit 6. So that was like the intro to hypothesis testing, but unit 6 and 7 are kind of one and the same because it's just the same stuff. You're just doing it more and more. Let me see. I don't know if I have room. Am I cool to erase this? Yes? Okay. It's gonna get messy. All right, so and depending on what type of data we have, will determine how we set up our statistic. So I'm going to do this. So right now we're doing 2 sample. Two sample means. All right. So I know I called it 2 sample means, but it's really just difference in means in a sense. And for this, we have 2 different possibilities. We have either matched pair data, or we have 2 sample data. So I'm going to set up the hypotheses just to show you the difference in the structure. So this is matched pair, and then this is 2 sample. So for a matched pair, we have the mean of group 1 minus group 2. For alternative, it's the same thing. I'm just going to do that for now. And then we have, for 2 sample, we have the mean of group 1 minus the mean of group 2. And then that's the difference here is that for each of these, we have individuals and observations. And for a matched pair, we have 1 set of individuals with 2 observations. So the way I like to describe it is that you have 1 set of people testing 2 different types of sneakers. For 2 sample, we have 2 groups of people testing the same pair of sneakers. 2 groups with 1 observation. So the difference between this is that this is taking, so in this case, I would say like pair 1 and pair 2, right? This is the pair of sneakers, the first pair of sneakers. This is the second pair of sneakers. And so what I would do is I would take, say, let's say they're doing the average rating of the sneaker, right? Like how they rate out of 10 or something. So I would take the difference in rating between the pairs, and then for each person, and then find the mean of that. Yep.
So matched pairs would be 1 group with 2 observations, and examples would be 2 groups, 1 observation.
Yeah. They're kind of like opposites in a sense. So I would take, so if I have like person 1 and they say 7 for the first pair and a 6 for the second, and I have person 2 who says 5 and 8, et cetera, right? However many individuals. So I would take the difference between these 2. So I'd have like a difference column. And this would be 1, this would be -3, ... And then I would add all these up and find the average of this column. So that's what this is doing. In this case, because we have 2 different people, we have group 1's rating, right? So for the first pair, for the pair group 1 says like 6, and then 7, 5. Group 2 says the first pair is better, so they say 8, 9, 7. Group 2 likes them better. So then we find the mean of this group and the mean of this group. So the mean, I know this is really low, I'm sorry. So mean of group 1 and the mean of group 2. Then we take that difference. So for a matched pair, we're doing the subtraction first and then finding the mean. For 2 sample, we're finding the means and then taking the difference.
Where does the, what's the rest of the no? Where's like the equal sign?
I'll get to that.
Okay.
I just wanted to show the difference in setup.
Okay.
So now that we have covered the difference, all of these are just always 0. So this would be not equal to 0, not equal to 0. So what they're equal to is the same, just how we set it up is different.
Why are they always equal to 0?
So if let's imagine that, like for this match pair example, both sneakers are rated exactly the same. So this number, if this is the same as this, it's going to be 0, right? So that means no pair is better.
Okay.
Whereas here, if it's not equal to 0, then they like one pair better than the other. Or there's a difference in the pairs. And then in the 2 sample example, if group 1 and group 2 like the pair the same amount, this is going to be 0. If group 1 likes it better than group 2, or group 2 likes it better than group 1, this is not going to be equal to 0. Yep.
With the 3 columns of numbers for the second one, like, are those different sneaker ratings, or are they just like 6, 7, 5? Are those all ratings for one sneaker for 3 different sneakers?
Yeah. So this is for one pair of sneakers. So like individual 1 in group 1 says 6. Individual 2 in group 1 says 7. And then individual 1 in group 2 says 8.
Okay, so it's broken down.
Yeah.
Okay.
And then we match each individual up. And that's how it's called. That's how we compare them.
Okay.
Does this make sense to everyone? A little bit better than before, hopefully. Okay. So once we have this set up, once we know what we're doing and which type of 2 sample or what type of difference it means we're doing, then we can calculate our statistic, which will always and forever be a t statistic. So, Michael, will erase this thing? Yeah? Okay. Okay. So, I'm going to just make match pair simple. So, both of these, we're finding what our t-value is. So, in the end, we're going to use the same table to figure out what our p-value is. For a matched pair, because we have one group of individuals, we're going to end up with one value, right? One mean of the difference, so to speak. So our t statistic is going to look a lot like the z statistic I just showed you. We're going to have x bar minus mu over s square root of n. That looks a lot like the one before, right? So in this case, this is our observed difference mean number. So whatever we observe from the population, or the sample, I should say. What is this going to be? 0, right? So technically, that doesn't exist, which is nice. And then this is the sample standard deviation and the sample size. Cool? It's just like the z value. Yep.
How is z different than t?
So for z is more of a population level type deal, because in the mean example before, we were comparing to a population. In this case, we don't know anything about the population. We just know about our samples, or our sample, so to speak. Yep.
Is it also that you use z when you have a sample size greater than 50 and the t minus 1?
Yeah, that's exactly right. Okay. So that's for the matched pair. If we have a 2 sample example, then where am I? It's going to look pretty similar to this, except we're just kind of like adding in our second group of individuals in there. So it looks like this, x1 bar minus x2 bar. And then I'm going to add this in minus 0. And then we have a giant square root. And we have s1 squared over n plus s2 squared over n. So we're just like adding another one to it, in a sense. So it's the same value, just computed differently. We good? Any questions about the difference?
We get both of these, right?
Yeah, so every time I write a formula down, it will be on the sheet. Because I'm taking it directly from there. So you will be given this, but you have to know what it means. There's no like, it doesn't tell you that this is match pair, and it doesn't tell you that this is 2 sample. So you just have to decipher. But it's pretty easy to tell, right? Which is which. Yep.
How did you know again that the mean is always 0?
Because that's our value in question.
Okay.
Yeah. Yep.
How many questions are on this test?
Maybe 80. So we're not, here in this case, we're not comparing to a population at all. These are 2 separate groups of people. So like over here, you have this mean of group 1 and this mean of group 2. And we're calculating their difference. This one? Yeah, so this is just the mean difference of this. So the average of this. We good? All right, so after you plug in all your numbers here and you end up with some value for t, you're going to do the same thing like you did with the z table, except there's a little bit more involved because we now have to take into account degrees of freedom, because that just accounts for the small sample sizes, etc., etc. So in this case, our degrees of freedom minus 1. That's pretty standard for a lot of things. In this case, we just figure out which one is smaller, which sample is smaller, which group of people. So n small minus 1. Because we always want to be conservative, so we never want to take the bigger one. We always want to take the smaller one. So then if you look at your T chart table that you'll be given, it looks a lot like the Z, where we have, instead of show, it does show 1 and 2, but again, we only really care about 2-tailed, right? 1-tailed doesn't really happen. So we have 0.2, 0.1, 0.05, etc., blah, 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 at the top. And then over here, we have our degrees of freedom column. So it's like 1, 2, 3, all the way down to some giant number. And then we have all the different values. So we have like 3.078, and then like 6.31, and then 12.706, etc., etc., etc. And so it looks like the Z table, except now we just have more rows happening. So the process to find our p-value is the same as we did before, except we're going to now go into our degrees of freedom. So whatever our degrees of freedom is, so let's say it happens to be 1. So we go to the first row, then we start going across, and we figure out where our t-value lies in here. So let's say I got a t-value of 8.3. Right, so that would be right here again, right between those. So just like last time, we are smaller than 0.1, but we're bigger than 0.05. So we would fail to reject. Nice and pretty. And again, you can see that the values get bigger as we go to the smaller side. Yep.
So for every, like, whenever we're using the tables, are we always gonna compare it to 0.05?
Unless told otherwise, usually. Usually the question will say, given an alpha level of 0.05 or a 95% confidence level. Those are one and the same. So if you look at the t-table, it also shows the confidence levels as well, but it's just whatever your confidence level is, like 95%, it's just 1 minus that to get your alpha. So if you're confused as to what is what. Yep. Yep, yeah. So whether it's two-tailed or one-tailed is decided by your alternative, whatever you put here. Cool? Make sense? All right. So now we're going to kind of segue into another statistic. So we talked about the binomial probability. We talked about one mean, and then we talked about difference in means. So binomial is you just calculate the probability. One mean, you use Z, and two means, you use T. So T is for two, T is for tiny, T is for a lot of things.
Can you say all of that?
Yeah, so for probabilities, you're using the binomial probability. For one mean, you're using Z. And for difference in means or two means, you're using T. All right. So now I'm going to erase this entire board. Is that okay? Good? I don't want to use that one because I don't think they can see much of it. I don't want it to get cut off. So the last big group of things involves categorical variables. And again, we can look at just one categorical variable or we can look at two. So the situations for these usually come from when people do surveys and you rate like something more than another, or you like pick your favorite subject. So if I asked all of you to take a survey and pick your favorite subject, then I recorded the results, that's where we get into this next category of testing. So kind of like the one mean and the two mean, we can have one categorical variable or two categorical variables. And these have different names. So for one categorical variable, this is called the goodness of fit. So one categorical. And the reason we call it this is before we do our survey, we have expected probabilities, like percentages for each one, right? So I could say, I think that people like all the subjects equally. And then, so that's my expected. And then I do the survey, and it turns out that not a lot of people like math, and a lot of people like science, etc. And I want to compare how well my results fit with what I expected. So that's why it's called goodness of fit. So for the hypotheses, our null is that observed equals expected. So if I were to do an example, like let's say there's math, science, English, and history. So if I think that people value those all the same, my expected would be like P of 1/4, 1/4, etc. for all of those. And then my alternative is that observed is not equal to expected. And this means that what I got from my results is just different from what I expected. So one category could be different, more than one could be different, they all could be different. We don't know, but we just know that if we conclude this, that they're different. And that people don't value it like this, in a sense. Okay, so now I'm going to kind of segue into the other one real quick. So the other way we can do this is for two categorical variables. And so this is called the test of independence. And so this is for two categorical. So for our hypotheses, our null is that the two groups, I'll explain this in a second, the two groups, or two groups are independent. I'll explain that in a second. And then the alternative is that the two groups are, I guess, not independent in a sense. So in this scenario, let's say I did the survey for a favorite subject, whatever, and I decide to split it up into males and females. So that's my two groups. So I have the males results, the females results, and I had what's expected. So if I expected an equal distribution, each one would be 1/8, right? They'd be equally distributed. And then I observe and I find out that, oh, more guys like science than girls, and more girls like math than guys. So I compare my results, again, to what I expected. And if the results come out and I fail to reject, and what I observed is similar to what I expected, then what our conclusion is that we can say that being male or female does not affect your choice of what subject you like. So if we fail to reject, if we reject, then being male or being female will affect your outcome. So that's the whole independence thing. So if they're independent, the gender doesn't affect the results. If they're not independent, gender does affect the results. Does that make sense? Cool. So no matter which situation, we're going to compute the same statistic. And this statistic is called the chi-square statistic. So it's usually denoted by an x squared, a fancy x. And what we do is we calculate observed minus expected, square it, and then divide it by the expected. And then we just add them all up. And this is given as well on your formula sheet. So, for example, I would say my observed percentage or my observed count for math was 40. And my expected was 25, if we're out of 100. So 40 minus 25 squared. And then I do it for the next subject, and the next subject, and then I'd add them all up. And that would be my chi-square value.
Yep, when you say subjects, you just mean like individuals or like?
Yeah, so let me see. So let's say I surveyed you guys, right? And if I make a table, I have expected and observed. Let's imagine there's 100 people in here. Make it easy. And I have 4 subjects. So I would expect 25, 25, 25, 25. Right? And then I do the survey, and I get back the responses, and I end up with 40, 10, 20, and 20. So the way I'm going to do this is I'm going to start with the first row and calculate 25 minus 40, square it, divided by 25. Then I'm going to do it for the next row, and then the next row and the next row until there's no more rows. Then I just add all those up, and that is chi-squared. Yep.
Is that what that weird little symbol thing means?
Yes, this is chi-squared.
No, like the.
Oh, yeah, this is the, this just means add everything up. It's the summation symbol. So do this for every single row, and then add them all up. And that gives you the value.
Do what when you add them?
So for row 1, I do observe, so 40 minus 25 squared and divide by 25. And so if this wasn't here, so I do 40, 25 squared divided by 25. And then I'd add the next row, 10 minus 25, etc. And you just add up all the rows, and that gets you your value. Yep. Yes. Yes. Yep.
Because it's two groups, like what you're observing, whatever, do you do that separately for each gender? Or is that like taking into account all people?
So yeah, so this table is goodness of fit.
Oh, that's a good.
Sorry, I put it over there. Yeah.
That's okay.
So let's imagine. So now I'm like all over the place. I'll do it here. So I do the same thing, but this time I split it up into male and female. Right? And then so this is math, science, English, and history. And so this kind of leads up to a different thing. So let's say I don't know what I expect. Like let's say I don't expect anything, I just do a survey, which is usually the case. And so I get my results, 5, 7, 6, 3, whatever. So now this table is my observed table. This is the observed. But I need my expected counts, right? So, and this is only for the test of independence. This won't happen with goodness of fit. Yep.
So is that chi-square value for goodness of fit, the one right below the test of independence?
This is for both.
Okay.
Yeah. It works for both. And I'll explain it in a second. So I need to calculate what my expected values are. And to do this is also on your formula sheet. So let's say I make a new table, and being very, very messy here. Male, female, math, science, etc. So the way that you do this is first you gotta just make sure you have your column and row totals. So let's say this is 50 and 50. And let's say this is 25, 25, and then we have 100 altogether. And let's imagine. So once you know what these numbers are, then you can use a formula. So to get the expected values, you do row total times column total divided by the entire total. And this actually works with this too, but it's kind of, you're just dividing evenly the distribution. So it's a little kind of not worth to do all this. But for two groups, you're gonna have to do this. And so if I were to do this cell here, right, which is this guy, so I would do the row total, which is 50, or that's column total, 50, and the row, which is 25. So I do 50 times 25, doesn't matter which order, it's multiplication. And then the grand total is 100, so this would be 100. And that would end up with my expected value of, I think, maybe 12.5, I think, that's what it is. Yep.
So calculating the expected values only for tested independence.
Yeah, you can do it for goodness of fit too, but usually it's given. Like, they'll usually say, oh, I expect an even distribution of favorite subject or something. And that should be pretty easy to calculate. Yep.
You're just like adding up the, like not the number of rows or columns, but like the values in them.
Yeah, so usually when you're presented a table like this, it will show the totals for the rows and columns, but you can fill it in yourself too if it's not given.
For the quiz, we have a question of, the expected value in this cell is 19, what is the value, like, if you formula, is that a kind of question we get on the test, where it's like, we get an expected value, and we start it on the answer?
So you're saying you were given this value?
Yeah, we're given, like, for instance, the expected for male, female, and math is 19, or whatever. And then it's, the question is, what is the value of the chi-square for the cell and table, and we plug it into the formula, right?
Yeah, so the value of the chi-square, so then once you get all these values, so let's say like this was, I think it ended up being 12.5 for each one, if I do it based on this. And so then I have my expected and I have my observed. So then I can do this thing. So for the males and math, my observed is 5, my expected is 12.5. So 5 minus 12.5 squared over 12.5. And then you'd go to the next cell. And then the next cell, next cell, next cell, next cell, all the way down. Then you'd add them all up, and that's your chi-square value. So instead of doing just like one row, you have to do cell by cell by cell by cell. Make sense? So you get this value, right? And again, you're gonna have to look at a table, which is fun. But again, we need our degrees of freedom. And so depending on which one we're doing, determines our degrees of freedom. So for the goodness of fit, degrees of freedom is just the number of categories minus 1. So that would be like 1, 2, 3, 4, minus 1 is 3. So we have 4 subjects, so our degrees of freedom is 3. For the test of independence, you find how many rows you have, then you find how many columns you have, minus 1, and then multiply them together. So if I were to write that out in a place, I guess I'll do it here, equals rows minus 1 times column minus 1. So in this case, we have 4 rows and 2 columns. So it would be 3 times 1, which is 3. So the degrees of freedom is the same in this case. Yep.
Wait, what does that say? The degrees of freedom equals?
The number of categories minus 1.
And you said, I'm sorry, this is about like a test. It's never gonna be like one-sided.
Yeah, yeah. And so this case, it's two-sided as well, right? Because we have the not equals. So that's a two-sided test. So once you have your degrees of freedom and you have your chi-square value, again, you just go down to the row where it's your degrees of freedom, go across to find where your value is, and then figure out what your p-value is and make your determination. So you can see that the process is the same. Once you figure out the statistic and or your degree of freedom, then you just look at the table and do the same thing every time. Any questions about all of that? I know that was a lot of material. Okay. So the last thing is just the 2 quantitative variables. I don't think there's actually questions about this because usually we use the software to answer the question. But the setup is very similar. The null is that the correlation or the slope equals 0, and the alternative is that it doesn't. If it doesn't equal 0, then our slope is significant, and there's actually a relationship between the two variables. That's pretty much what that says. For that, we'd also use a t-statistic as well. So if you got your t-statistic, then you'd look at the table, figure out your p-value, and make your conclusion, as we've been doing multiple times. Yep.
Wait, so if it doesn't equal 0, then what happens?
So then the relationship between the two is significant. Like there is a relationship between them. Yep.
Can you just like repeat that again?
Yeah. So our null is that there is no relationship. So the slope would be 0. The alternative is that the slope is not 0. So there's some positive or negative relationship between them that's significant. Yeah. All right. Any questions about hypothesis testing? Because actually the correlation slope thing is a good segue into Unit 3, which is cool. All right, I'm gonna transition to Unit 3. So in this unit, we talked about, again, the relationship between two variables. And I'm going to erase the board and talk at the same time. The way we did this is we started by making a scatter plot, right? So we had our x on the lower axis, and then our y on the upper axis. This was also known as the x variable was the predictor, or the independent variable, and then the y value was the outcome or the dependent variable. It's like an arm workout, jeez. So we would make a scatter plot, right? So this is our x, this is our y, and we have a lot of dots doing something, right? And then we'd use the software, and it would make a magic line for the data, right? So the way this line works is that it takes each data point and it calculates a residual. So the difference between the predicted value and the observed, right? Again, this is expected minus observed. We've seen that before. So what it does is it takes each data point and figures out the difference between each one. And the software figures these out, does a lot of math, and it tries to figure out the best line to minimize every single one of these differences. So it's super intense. Once it does that, it can plot the line, and we get an equation. So usually in the form of y equals something times, something times x plus something, right? We've seen this before. This is our slope, and this is our intercept. Hopefully this is like 7th grade for most people. So there's actually formulas to calculate all of these. So if you have the formula sheet, then you can look on like the 3rd or 4th page somewhere. So in this formula here, it says that this is A and this is B. Right, so our slope is B and our intercept is A. And it shows different formulas for how to calculate these if you don't have like the software to do it. So to get our slope, that's B, my bad. B, it looks like this, S, Y over S, X. So this little r here is our correlation, which I'll show the formula for in a second. And then this is just the standard deviation of the y variable divided by the standard deviation of the x variable. So in like R or whatever, our data set, we have the list of all the x's, we have a list of all the y's, and you can calculate your standard deviation for each one, and then you take the division of that, multiply by the correlation, that gives you your slope. I'm only showing you this just so you know what each thing means, so that when you look at the sheet, you're not like, what are these letters and numbers? To get the intercept, so this is the first thing you'd have to do, given that you already have the correlation. Then to get your intercept, you would take the mean of y and subtract the slope times the mean of x. So you have the list of y's and the list of x's. Calculate the mean of both the y's and the x's, and then you just take y, mean of y minus the slope times the mean of x. Yep.
Can you just quickly like say how you find the standard deviation of like the y or x variable?
It's on here somewhere. So on your formula sheet before the correlation part, it shows the standard deviation formula as S square root 1 over n minus 1 super scary. This, so if we were doing SY, so then this would be Y bar and YI, and this would be the sample size of Y. So 1 over n minus 1, that's easy, right? How many things you have. The summation symbol, we've seen that before. And then this is just taking every individual data point and subtracting the mean of y. So it's finding like a difference for every data point. And then you just square each one and add them all up, divide by this, and then take the square root. So it's a lot of math. Yep.
So like for the most part, we'll be given the standard deviation.
Yeah. I don't know if he'll have you actually calculate a standard deviation. If he does, it might be only like three points or something. But again, I'm just trying to show you like what this means, so you're not looking at the sheet and being like, what? I don't know what's happening.
Yep. The summation symbol, do you like after you other ones, do you then like have that factor and then you add it to the multiplied by the 1 over n minus 1? Oh.
Yeah. So this is kind of like its own little thing, and then you do the rest. So that's how you get the standard deviations. I'm pretty sure everyone knows how to find a mean. Pretty easy. So everything's kind of built off everything else. So I'm going to actually show you the correlation formula real quick. Where is it? So first you find your mean, then you can find your standard deviation. Once you find your standard deviation, then you can find the correlation. So that's a little r. This is a really big formula. So once you know this, so you do this for both y and x, right? And then you can plug those in here. And again, we're taking this like difference between each point from the mean. Do it for x, do it for y, multiply them together. And this is just saying like you add all these up, and multiply. So it's like summing this, and then multiplying. It's just easier to write it this way. Wait, I said that wrong. I'm sorry. So you do it for like data point 1, right? So person 1 has X and Y. So you do this, multiply them together, and then you do for person 2, person 3, person 4. Add them all up. I know this is a lot of words in math. So once you add them all up and do it for every single person, then you do the magic n-1 division thing, and that's how you get the correlation. So then once you get the correlation and you know your standard deviations, then you can calculate the slope and intercept. So it all kind of builds up on itself, and it's really complicated. And that's why software is awesome. Because on all your homeworks, you would have had to do this for like the entire homework grade. Yep.
Gonna make us do this.
I'm not 100% sure. I don't think it's going to be like involved. Like you won't have like 50 data points or anything like that. If he does do an example, it'll be like maybe 4 points or like 3 points. But I think he just wants you to understand what this is. So like if I showed you this formula here, you should be like, oh, that's the correlation or something. Or this is the standard deviation and where it comes from. All right. So you find your slope, find your intercepts, then you have a magic formula that can predict. So if you are person X with something X, it can predict your Y. So if you're this age, I can predict your weight. Or if you're this tall, I can predict how much food you eat or something. I'm trying to think if there's anything else. Are there any questions right now? I know I'm in the way of the thing. We good? Yep.
There's just like an example from the final exam practice questions thing that I feel like I don't really. It's about the least squares regression line, but I'm not sure.
Is it Professor Staub's practice questions?
It's
Okay.
It's number 14.
Okay. What set is it in?
Oh, no, second. Sorry.
Okay. I think I got it. Okay. So this is basically doing these formulas. So this line has many different names. It's called the line of best fit. It's called the least squares regression line or the regression line. Those are all common names for this magical line that tells us stuff. So in question 14, I don't know how many people have the thing, but let me see. I'm going to erase this. So consider n pairs of numbers, and the mean and standard deviation of x are 5 and 4. So x bar is 5, and sx is 4. Then it says the mean and standard deviation of y are 10 and 10. So of the following, which could be the least squares regression line? So, and then it gives like a bunch of answers. So if we were to calculate our least squares regression line, I'm going to kind of consolidate that a little bit. And so we'd have y equals r s y s x times x plus y bar minus b minus r s y Sx x bar. So what I just did here is I just plugged in these two into this. And so I made one giant formula. So if I do a little bit of math, so this is the same as this, right? So we don't need these parentheses. So we have R S Y S X X minus X bar. You see what I did there? I pulled out this R and then I had X minus that. Right? Good. Plus Y bar. Does this make sense? A little bit? So let me pull up grab this again. So let me just look here. So we know that this, so if I were to replace everything, SY is 10, right? SX is 4, X bar is 5, and Y bar is 10. And the correlation we're not too sure about because we don't know what each individual point is. So, trying to do some math here. So this is 2.5, right? 10 over 4. Yeah. So this is 2.5 sum R times X plus, so I'm putting this back in now. 5 times 2.5 is 12.5, right? Yeah. 12.5 R plus minus mod B minus and then plus 10.
Where'd you get the 12.5 from?
So that's 10 over 4 times 5. Sorry, it's really low.
So are you like going back?
Yeah, I'm
to-
factoring it back in.
Okay.
Yeah. So if we ignore our correlation for a minute, which one of these could be the equation? Let's see here. I'm trying to figure out where he got the correlation from. Would have been useful if I looked at these before doing this review session. Let's see. So, of the different options, so this would be our slope, right? 2.5 times R would be our slope. And then this would be our intercept, right? That's really, all right, hold on. Nobody can see. So what I have here is y equals that better? Okay. So this would be our slope, and this would be our intercept, right? So the options are, I'm going to quickly write these out. 5 minus 3x, 3x, 5 plus 2.5, x, 8.5 plus 0.3x, and 10 plus 0.4x. So which one could it be? It has nothing to do with what R is. That's kind of a hint. Yep. Okay, well, I appreciate the guess. So this one has a negative number, right? And I'm going to check the answer here, so I'm not doing the wrong thing. Okay, so trying to figure out what he did here. All right, so I'm trying to figure out how we got this correlation because obviously this isn't an intuitive answer. Let me just try something real quick. 40. All right. Let's see. So the correlation can be between -1 and 1, right? We learned this? Yeah? So if our correlation was 0, we'd have y equals 10, right? I'm trying to brainstorm here, so. Because if this is 0, then all that is 0. If this is 0, this is 0, so we're left with 10. If our correlation is 1, then we have 2.5x minus 2.5. And I don't know where he's getting this from.
On the answer key in the back, there's like an asterisk next to it and like a dash and like the when it's like has the full numbers on it. Like this one back here, it has like a thing for this number. So I don't know if that means like
Yeah.
how it is.
Okay. It'd be nice if you had explanations as to why it's there. And so for -1, I'm just trying to.
Can you come back to this at the end?
Yeah. I'm not really sure why or how that's the answer. Okay. Sorry about that. This is what happens when you're not prepared. Okay, so basically I wanted you guys to just see how these formulas work and understand like what each thing in the formula means. So hopefully if you look at the formula sheet, you're not like, what is the correlation coming from, or like what is the standard deviation coming from. So just a few things that you should know. So the correlation is from -1 to 1. And so if our correlation is positive, then the line is positive, right? The slope is positive. And if our correlation is negative, then the slope is negative. And the association is negative. We can then get an R² value. I'm going to get rid of this gibberish. So we can get an R² value, which is literally R², just the correlation squared. And this number tells us the proportion of variance in Y that can be explained by X. So let's think about this a little bit. If our correlation is 1, right? Trying to base it off the slope. So if our correlation is 1, our R² is also 1. So if our correlation is 1, that means that everything about Y can be explained by X. If our correlation is -1, that's also the case, but it's a negative relationship. If our correlation is 0, R² is 0. So because there's no association, we can't explain Y at all. Make sense? So when we're doing regression lines and regression slopes and all that fun stuff, we always want our R² to be big, because that means that there's explanation for our relationship, and there's less that we don't know about. So if I have my line here and all my points, and R² is based off of the difference. So if I took this point here, and the mean of Y is like here, so R² is based off of the differences for that. And then if I did my X, the mean of X is here. R² is based off these differences as well. And then there's some standard deviation thrown in, n-1. It's magical. So if our correlation is big, that means that there's not a lot of variation here. So these are like super tiny, and it's a really skinny plot of scatter points, which means that the variability is very explainable by X, because we're very close to this line of best fit here. So our R² value in this case would be really, really big. But if the points are like all over the place and you can't really see an association, then X isn't explaining Y that well, and R² is going to be really small. Make sense? Ish?
So if there's a small R², the variability is explained by, and Y is explained by X.
There's not a lot. So R² in itself is the proportion of variance explained in Y by X. So if R² is 0.2, 20% of the variability is explainable. And we don't know why the rest is why there's the variability. If R² is 99.9, which really will never happen, that means 99.9% of the data the variability in the data is explainable because we know about X. And there's that one little percent, 0.1%, that we don't know. That's uncertainty. Make sense?
Can you explain like you went briefly like in that unit about heteroscedasticity?
Heteroskedasticity.
Yeah.
So-
Because I remember in the quiz online there was like probably questions like, oh, what brass pertains to, like what it looks like. I know it's kind of curvish.
Yeah, so let me just say, so this involves the residuals.
Yeah.
So you guys remember that you were able, based off this normal scatter plot here, you were able to make a plot of the residuals, right, around 0. So if I draw some sense of that, so here's 0, and then we have all our residuals, blah, 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 and so there's really not a lot of change in variance. So what we look for is if our distribution is normal, this is going to be like, there's going to be no pattern you can see in the residuals. All right, so the variance is not changing, right? It's not skinny on one end, it's not big on the other end. There's no like curve or like line of residuals. But if we have it very skinny on one end and super big on the other, so we can kind of draw like a bell shaped thing, that is heteroskedasticity. If you see a plot that looks like this, so if I drew lines around the residuals and it looked like that, or if it looked like that, that's not heteroskedasticity. So it's only if you see that cone shape or bell shape. Cool? All right, where are we at for time? Wow, it's going by. Only half an hour left. Okay, so I wanted to cover confidence intervals a little bit. Does that seem fair to everybody? Yeah? Are there any objections to that?
I just have a question.
Mhm.
Could you give an example of the difference between ordinal, integral, and ratio?
Yeah, okay. I'll try to do that super quick. I'm gonna erase this by random formulas. All right. So, I'm trying to think, it's hard to do one on the spot, but I'll do my best. So, ordinal is, so let's say I give out a survey and I want to have you rate how much you learned. Like, did you learn a lot from this review session? So you'd have like, I learned nothing, I learned a little, neutral, I learned a lot, blah, 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 right? So you have like the 5 things. So that would be an ordinal variable because you can put them in an order. And there's not necessarily from highest to lowest or lowest to highest, right? But if I said like, don't agree, somewhat agree, neutral, etc., etc. I'm not going to put neutral in between these, right? Like there's a natural ordering to which way they should go, but there's no one that's better or worse than the other. Does that make sense? So, interval. Trying to think. So interval would be that, I'm trying to remember. So if I had like a rating system for cars, so like 1 star, 2 star, I'm trying to think of a better.
Is it temperature?
Yeah, temperature.
Yeah, so temperature is a good one. It's also like the easiest one to explain. So if I'm thinking in degrees Fahrenheit, right? So let's say I have 0 degrees, 20 degrees, 40, 60, 80, whatever. So interval is a subset of ordinal. That's how I like to think about it. So there is a natural ordering, right? But the difference is that interval, now the differences are meaningful. So 20 to 0 is the same difference as 40 to 20. No? Huh? You're shaking your head. Yeah.
I don't know how to explain, but I disagree with that. It's not same.
So
I mean, it's like 20, there's 20. How can I say?
so is
Because the meaning of like old degree 20 and 20 to 40 degree means different.
yeah. So
So it
But
cannot
they're
be
all separated by 20 degrees.
yeah. So like if I took this interval and this interval, there's the same amount of degrees
Yeah, sure.
Fahrenheit in between.
Sorry.
So I could say like if today was 60, right? Today was 60 degrees, and tomorrow's 80 degrees. Tomorrow's 20 degrees warmer than today. But I can't say that I'm more agreeing. You know what I mean? Like that doesn't make sense. So heat, like the heat is not 20 like the same, but it makes sense to say that today's 20 degrees warmer than yesterday or something. Now the difference, everyone knows what Kelvin is, right? Kelvin's like absolute heat, right? Or whatever. So 0 degrees Kelvin is no heat at all, right? But 0 degrees Fahrenheit does not mean there is no temperature, right? So this is where we get into ratio. Ratio means that you can actually say there is an absence of something. Does that make sense? So I guess you could say, like, if I were to put it all in the same context, so if I were to say, what was the temperature today and what's the temperature tomorrow? Today it was warm, tomorrow it's hot, but I can't say it's so much hotter. Today was 80, or today was 60, tomorrow's 80. So tomorrow's going to be 20 degrees warmer. If I go here and I say like 100 degrees Kelvin, this means no heat at all. There's the absence of heat. And you can still say there's 100 more degrees Kelvin of heat today than there was yesterday or something. So they're kind of like subsets in a way. So this is like the more general. And then we get into a little more specific. And then we get into like specific, very specific. Does that make sense for everyone? A little bit more than it did?
So the biggest difference between interval and leisure is the meaning of 0.
Yes. Yeah. So going from ordinal to interval, the differences between each thing are meaningful. Going from interval to ratio, now our 0 is meaningful. You good? Cool. All right. Confidence intervals. All right. So let me see if I can find it. There it is. So on the formula sheet, it gives you like 2 different types. I'm gonna write them out. So he gives and he gives so this is what's good on your formula sheet. He gives this one and then he gives this one. So the first big difference is our critical value. Right? So these are based off the Z table and the T tables that we were talking about with the hypothesis testing. So if you look at the chart for the T table or the Z table, you'll get the critical values that you should use. But I think the first thing he shows on the formula sheet is like critical Z for CIs, and then on the T table, the way it works is, trying to look here. So if you were to find your T value, then you'd have to take into account your degrees of freedom here. Right? So you don't have to worry about it with Z, because this is for big sample sizes. So this is n bigger than 50. This is n less than 50, and then degrees of freedom n minus 1. Yep.
For both of them? Wait, never mind.
So that's the first thing you should do. You should be like, is my sample bigger than 50 or smaller than 50? That tells you whether to use Z or T. So depending on which one you pick, and depending on your confidence level, usually it's 95. You'll get some value for Z. I think Z is 1.96, and then T depends on what your degrees of freedom are. But usually it's like, I've seen it be like 2 point something, usually, depending on your sample size. So the other difference I want to kind of just point out is the standard deviation here. So the reason we have sigma is because our sample size is big, we can assume that the sample is similar to the population. So this technically is an S, but we're assuming S is equal to sigma. Does that make sense? And we can do that because we have a big sample. Because we have a small sample, we have to use the sample standard deviation. We can't assume that it's equal to the population. So you figure out what your interval is based on your mean, critical value, standard deviation, and sample size, and you're going to get something like this, where here's your X bar, right? And then you have your interval here and interval here. So before I go into that, I'm kind of all over the place, I'm sorry. The breakdown of this, so this is your mean, right? X bar. This little chunk here is your standard error, or standard error of the mean.
The Z?
No, the sigma ran part. And then this giant chunk, so everything you're adding and subtracting, is the margin of error. Because it's the margins to where you go.
What's the margin of error?
Everything to the left of the addition and subtraction. Yep.
How'd you get sigma? How'd you get sigma?
Usually it would be given.
Okay.
Yeah, so they'd say like the sample standard deviation is this, Be careful. I think there's some questions where they'll say that the sample standard deviation is this, the population is this, and our sample size is 20. So because your sample size is 20, you wouldn't use the population standard deviation, right? You'd use the sample. So make sure that if we have a small sample size, that you're always in sample land, never population. If our sample is big, then usually it'll say the standard deviation of the sample is this, but you can assume that it's equal to the population one. So this thing is your standard error. This thing is your margin of error. And if you add and subtract to the mean, you get your interval. And so we know that 95% is inside here. And that means there's 5% outside, right? So this kind of relates back to the hypothesis testing, where if we're inside our interval, then we are bigger than 0.05, right? Because 0.05 is right here. So if we're inside, there's more percentage outside. So we're bigger than 0.05. So if we're larger than 0.05, we would fail to reject, right? So that means if we're inside our interval, we will fail to reject. And then the opposite is true as well. So if we're out here, we're smaller than 0.05, which means we'd reject. So if we're outside of our interval, we reject our hypothesis. Yep.
So what if it was like just like this is general, if it's like the p-value is exactly 0.05, would you still reject it? Or would it be like a different case?
That's like the gray area of stats. You'd probably want to run your test a couple more times and see. But in a statistical world, we tend to be conservative. So if it's like right on the mark, we'd usually fail to reject because it's not like small enough to actually matter. Okay. Any questions about this? Yep.
So if you were to say like test for the confidence interval on like 90, you just would use one point, like you'd use a different value.
Yeah.
96.
Yeah, so on your, I think the first page of the formula sheet, it gives you the critical values for Z. So for 90, we'd use 1.645, and if 99, we'd use 2.576. Any other questions? All right. So let's see. We've covered hypothesis testing. We've covered slope and regression. Yep.
I don't remember what chapter this was in, but it was like 60, 90. Well, can you go over that?
Yeah. So actually, that was in my confidence interval section. So actually, based on this, so we know that for 95 we use 1.96, right? So this is for Z is based off the normal distribution. So if our distribution is normal, we can make assumptions about what our data looks like. So actually, let me just cover.
What's the 1.96, the Z-score?
So that's the critical value for a 95% confidence interval. So we learned about two different types of distributions, right? We learned about a binomial distribution, and we learned about a normal distribution. So the binomial distribution is based off integers, right? We can't have like 2.5, we can't have like 3.7. So think about rolling a die, where if we roll a die 50 times, we expect it to have some, well, this is not the right thing, but we have a probability of getting 1 out of 50. So if I have a line here, that'd be like that much. We have a probability of getting 2 out of 50, which is a little more, and then looks something kind of like this. That's usually what a binomial distribution looks like. So each of these lines is the probability of getting so many out of so many. So an easier example would be using a coin flip. So if I flip a coin 50 times, these are all the probabilities for getting so many heads. So 30 out of 50 would probably be somewhere here. And then 25 out of 50, we expect 50-50, so 25 is probably the highest point, right in the middle. If we expected heads to come up 75% of the time, this would look a lot different. So it'd be like something like that, and 75 out of 100, whatever, would be over here. This is making sense. So the distribution is affected a lot by what we expect, or what our expected probability is. So that's a binomial distribution. It doesn't have to be symmetrical, and it doesn't really have any special rules. It's just each point has a probability, and around what we expect usually has the highest probability. Now, for a normal distribution, it has some nice properties. So normal distributions are symmetrical around the mean. And it also has this rule about the 68, 95, and 99.7 percentage. So I'm going to redraw this a little bit. So if I have a normal distribution, I'm getting really good at driving, with some mean x bar, right? You've seen this? So if I go x bar plus 1 standard deviation, and I go x bar minus 1 standard deviation, and I draw a line, 68% of the data will be in this interval. And then if I go x bar plus 2 standard deviations, and x bar minus 2 standard deviations, that's our 95. And we learned in reality it's actually 1.96. So this is, as always, approximate. It's never going to be perfect. But if it's close, then we're pretty much normal. And then if I go 3, so if I do 3 and 3, that's 99.7% of the data inside. So if I were to do like a 99% confidence interval, that's about 3 standard deviations away, in a sense. It's not exact, but math-wise, it makes sense a little bit.
What was the percentage of the second one?
60. Yeah, so
68 for the first. Yeah.
68, and then 95, and then 99.7.
Thank you.
And because this is symmetrical, we can split these up so we can figure out what percentage are in these intervals here. So if I just do from the mean to 1 standard deviation, that's 34, right? Because that's half of 68. And then if I go from the mean to 2, that's 47.5-ish. Yeah?
Isn't that, so that little chunk right there is 13?
Yeah, this is like 13 point something. Yeah. Yep.
It's that 3 number.
Step 3, number 7. Cool. So do you want me to just go over it, or do you have a specific?
I didn't know whether you had to use a G or T score because I knew it only had 4 rows, but when I tried doing a T, it didn't work. So I couldn't figure it out.
Okay. So I'm just gonna read this off. Summer resort rents rowboats to customers does not allow more than 4 people to a boat. Each boat is designed to hold no more than 800 pounds. Suppose the distribution of males who rent boats, including their clothes and gear, is normal, with a mean of 190. So let's draw this out a little bit. So X bar is 190, and a standard deviation of 10. If the weights of individual passengers are independent, what is the probability a group of 4 adult male passengers will exceed the acceptable weight limit of 800 pounds? So we have 4 passengers. Each passenger is expected to weigh 200, right? So if any passenger is more than 200, then we're over the weight limit, right? So for 1 passenger, our mean is 190, and so if we're at 200, that's 1 standard deviation up, right? So that's 200 there. And this is a normal distribution. So we know that 68 is in here, right? It got really empty. Wow. So if we're over 200, then this is like, we said this was 13, right? This little chunk, right? Because we have 68, and then we go to 90. 90 minus that is, or 95 minus that is like 28. No, 95 minus 68. 23. 27. All right. Yeah, so this is 13.5. And then we are left with our last one here. So we know that this is a lot of math, I know. Might help it. Okay. And then our last, so this is 210, 220, 180, 170, etc. And so 13.5, 13.5, and then we have 99.7 minus 95 is 4.7. Divide that by 2 is 2.35. 2.35. And then outside of 99.7, we're left with 0.3. So half of that is 0.15. That's left over, right? I hope I'm doing this right. So we care about over here, right? Because if they're more than 200, that's danger zone. So the probability of not being over 200 is 68 plus this, plus this, plus this, I think. I don't know what that number is in my head. 68, 14, so 82, plus 3, 85, so like basically 85. So this is about 15%, right? Give or take. So the answers that were given are 0.023, 0.046, 0.159, 0.317 or 0.977. So if everything this way is 15%, the answer would be C, I think, right? Is it? Of course.
Is there like a formula you can use for this type of stuff?
Yeah,
I
it's
don't
just
understand.
like-
There's a lot of questions on there that are like you need a formula for, and I don't know like what formula to use.
Okay. Check
I'm
out.
assuming that's one of these people, but I just didn't know that you do.
Okay. So I really should have looked at this before doing this, but so if the weights are manufactured are independent of ability going forward. Okay. So now I'm getting confused too.
Are these like practice problems like he has given us right now similar to the, I guess,
Yeah, that's what I'm nervous about.
because he did say these were from like people.
Yeah. Let's see.
Just like never did these type of problems in class, so it's really frustrating. But
Yeah.
I don't understand why you test on things that we never learned.
So I'm just trying to process this. Okay. I know what this is. Okay. So I have a feeling this is a chi-square question. So let me try to walk through this real quick. So we have 4 people, right? And trying to think if this is what it is. Nope, it is not. Just kidding. I'm sorry. They're independent. Before it out my house. Okay. What's 0.15 times 4? Or times itself 4 times? Because this is for one person. So the probability of being over for one person is 0.15. So we have 4 people. So that means we have to take into account each person.
About 0.0005.
Okay. I'm probably overestimating this. So if you figured out, so we got 13.5, 2.35, and then 0.15, I think. No. Yeah. So if we add these up, we get 2.5 plus 13.5 is 16. So it's actually 0.16. Lots of math, I know.
0.0006.
That's still not the answer. I'm honestly not sure about this. And so I guess what I'll say is that last semester I got to look at the exam before, and like he made us like take it to see if it was too hard, and I was able to like take it okay, and I know that I'm like up there with the stats, but I think the fact that this is stumping me is kind of saying that based on what I did for the exam last time, I wasn't stumped by anything. So I think these are like harder than what he's given.
Okay.
I wouldn't worry too much. I think as long as you understand like when to use what in a way, hopefully me kind of covering what like the formulas mean and everything helped a lot. Just trying to so I wouldn't worry too much about this practice exam. Yeah, I know that didn't really answer your question.
Okay.
Okay, so it is 3 o'clock, and does anyone have any outline questions? Yeah.
Just on like looking at what you did for that, how'd you get the 13.5 and the 2.35 again? Like you started out with 68.
Yeah.
Because
So what you do, because I know that 68 is 1, 95 is 2, and 99.7 is 3. So if I know that 95 is this part, and I know that 68 is here, their difference is 95 minus 68 to get this segment.
Oh, okay.
And then I split it in half.
Okay. And can you use a graphing calculator in this exam? Like, does that matter?
I think it should be fine.
Okay.
Yeah.
Cool.
Any other questions? All right, I guess that's it. Thank you guys for coming,
Thank you.
and hopefully this was helpful. I'm sorry I couldn't answer some things, but that's life, I think.
I just have brief questions. So how many questions on the exam is it almost?
It's all multiple choice, and I think there's 80.
80.
Yeah. But they're not each going to take you like a minute. You know, some are going to be like, I know this right away. And they're not all like super computational.
Okay. So can I allowed to use the calculator?
Yep, you can bring a calculator.
And I have really quick question. So in this situation, the median means I knew that like mean is greater than median because it's the screen. I mean, I'm sorry.
Yeah.
Right, the right screen, right?
Mhm.
Yeah. But in terms of this case, is it like median is greater than mean? When
Yeah,
it's like
so,
downstream?
yeah, you can think of it like the tail pulling the mean away from the middle.
Yeah, true.
Yeah.
Okay, got it. Thank you.
Yep.
This one is kind of the one that we were just doing, but.
So, let's see, 80 is middle, so 60 is 2 below. So, yeah, so this is if you take, just have to redraw this thing one time. So, the average distribution, and our mean is 60, right? Or 80. And we're looking at 60. So that's 2 standard deviations. So we know that if I went the other way, then we have 95 in the middle. So we have 0.05 total outside. So half of that is 0.025.
Okay, and then my other question is just looking at. Looking at this, okay, this question.
Okay.
So for this one, do subtract 1 for that, so you look at 23,
Yeah.
right? And then it's 1.78, so it's in between these two.
Yep.
And it says the answer is less than 0.05, but that's usually the one that says test.
You know, saying
It might be a typo. I made this like didn't check it.
Because you always
Yeah.
use the two. Because
Yeah.
I thought it was, because if you.
So wait, hold on. What's our value? 1.78?
Yep.
So we're in here.
Yep.
Like go up. Okay. Yeah, I think that's a typo.
Okay,
So it should be less than 0.1.
Okay, perfect.
Yeah.
Thank you.
Sorry about that.
No, no, no.
I just have a question about the answer key.
Mhm.
It's kind of confusing. So the numbers are like all out of order, but
Yeah.
so I guess I was just wondering for 2. That's definitely B. That's not A.
Well, that's question 5.
It's the second one in order. Is it still question 5 on the?
Yeah. So in the answer key, it would be like, because he didn't include all the questions for that answer key.
Okay.
So like question 2 on the answer key is for number 2. Like the one that's denoted number 2.
Okay. So this.
Would be number 5.
So it's A, and it's 7, just because it's 8 minus 1. So that, it's the.
Yeah.
And if I have any questions, like, should I be studying this? Like, is that
Yeah, I would.
the gist of it?
Yeah, I would check out the quiz questions
Okay.
on Moodle. Those are usually pretty well. That's what I made this like another mock-up test from.
Yeah,
Are you my?
I'm not.
No.
That
Okay.
was last semester.
Okay.
How it goes.
Yeah. So I'm happy to send you this if you want,
That'd be awesome.
and
I'll,
just send me an email and then
okay.
yeah.
All right, thank you.
Hey, this is just a really stupid question, but I was going through my slides yesterday, and this was one of the questions, and I like, it's so simple, but I just like didn't know like what I had to do for that.
So unit 4.
Like finding the probability of value, and you're given the mean and the standard deviation.
Was there anything else on the slide, or just the?
It was just the question, yeah. You can Google the problem with that, I'm sure I could like.
Oh, okay, so this is, going off the 90, 68, 95 rule. So our mean is, what's our mean?
18,
18?
and 2 standard deviations off.
Yeah, so then, so 1, alright,
Okay.
standard deviation is 2.
Yeah.
Okay, so going 1 standard deviation would get us to 20, right? So we know that 68 is 1 away, so half of 68.
Is 34.34. Okay, perfect. Thank you so, this was so helpful. Thank
Yeah,
you so
no
much,
problem.
really appreciate
This
it.
is for the probability chapter, right?
Well, this is based off the normal distribution, but it's binomial and normal are in the same.
I have a question.
Okay, so when we talk about, like we make the scatter plot, right? So we have, so when we do this, the scenarios usually we say we have some variable x, and that tells us about something about y. So x predicts y, so that's why x is the predictor, and y is the outcome from x.
Oh, is it?
Yeah,
Oh.
yeah.
And then like, it's categorical or quantitative? Like how?
So it's quantitative usually if you have like, like age. So age is like someone's 23, someone's 42.
Yeah.
Quantitative
is like, I'm sorry.
Yeah.
Sorry.
Yeah, so quantitative is like a range of numbers. Categorical is like, if you'll see it in the data where it says like 1, 2, 3, or 4, or like 1 and 2 for like gender. So there's no like meaning to the actual numbers.
Right.
Yeah.
Okay.
All right.
Sorry, I should ask about this during the discussion, but, so I don't really couldn't figure out why we should use G-score and what is G-score exactly? How can I define it? Like,
So, okay, so when you look at populations and you look at something, so let's say I look at the population of Europe and then I look at the population of the US and I'm looking at age, right? So Europe is going to have some distribution of age with some mean, right? So let's say their mean age is like 30, let's say. And then the US has a different distribution with a different mean. So their mean is, let's say, 35. So the reason we use the z-score is so that we can compare these two with the same mean. Because
comparing
populations.
comparing the population.
Yeah.
And the same mean.
Yeah, so when you standardize everybody, so when you standardize everyone in each population, you're going to end up with a mean of 0 and a standard deviation of 1. So both populations are going to have the same distribution. So then we can compare them.
To make it fair.
Yeah.
Oh,
Yeah,
I
yeah,
got
yeah.
it. Oh, I got it. So.
Yeah, I know, it's a lot.
I mean, like during whole semester, I was fine for the homework and quizzes because I could understand. I'm sorry.